exactly. And then this will be put on YouTube, so you can watch it later on. Okay. So this is Trustworthy Machine Learning lecture. So if you're mistaken, then you can change the lecture room now. Yeah, my name is Song Juno, but you can just call me Jun because that's easier than the other syllables here. Yes, I'm recording video now. So these are some motivation slides for why do we care about trustworthy machine learning. So this is a very iconic plot of how machine learning, or more specifically computer vision, has improved over the years. Hello. So it looks like there's been some improvements, and it's going towards 100%, right? Which is good. And there are nowadays something called scaling laws. So if you grow the size of the network and grow the number of data points, then you will actually get better results. So does that kind of answer all the questions, remaining questions for machine learning? Right. So it looks like we're kind of reaching we're going on a very good trajectory towards a very good performance of machine learning. But then at the same time, we're kind of seeing the non-universal use of machine learning in real world, where machine learning could still benefit. Sorry, hello. A lot of applications. So now the question is, why do you not see machine learning in every business? Because that could clearly help out a lot of business applications. And also we don't really see, well, we see some of the changes in our life because of large language models, but we do not see it's to change as much as we like so far. And we also haven't seen like quantum leap in productivity that could be seen in the GDP or any economic indicator yet. So here the question is, what are the remaining challenges of machine learning? And what are the ways to capture the remaining challenges in machine learning? Okay. So one biggest hurdle in machine learning application is that it's very expensive to use. So we have a hypothetical situation here where someone owns a restaurant, and the owner wants to predict the demand in the future. What is the right amount of ingredients to prepare for tomorrow? Let's say there's like a school event in a nearby school, so maybe you're going to expect you expect more students to come tomorrow. So how much ingredients should you prepare in order to minimize the rest leftover, right? But then to do this kind of thing, you need some machine learning expertise, which is not cheap. One option is to hire a machine learning engineer. But you know, like when you wish to hire them, they are like 100K euros or dollars per year. So are you really going to hire them full time, right? The other factor is, the other possibility is to learn it by yourself, but then you have to go back to linear algebra and start from there. You can also use machine learning cloud, but I'm not sure if you have used the SageMaker and these similar services, but these are very expensive in general. Several hundreds of euros up to could be also thousands of euros if you're using in full. So also, it's not just compute, but also data tends to be expensive. You can choose to collect by yourself, but then you need to have some knowledge of database and schema. Well, you can learn it by yourself, but it takes time. And also, if you want to collect it, you have to collect it for some time period, and that takes quite a while. You can use public data, but public data are not, in general, suitable for your application scenario, right? And it's very challenging to find some data set which suits your needs perfectly. You can also buy some proprietary data or ask some data collecting agency to do the collection for you, but they're expensive. The other limitation is that machine learning models tend to not generalize very well in some new situations. So you always have to either collect data from your target scenario or you just hope that it works in the new situations, right? Also, if the model finally works, there are some remaining trust issues because, like on paper, it seems to work well, but then eventually, the question is whether you're actually going to use it or not. And if you're not trusting the model, then you're probably not going to use it. And this is typical when a lot of things are at stake, like money, health, or your life, right? So in these situations, even if the model performance is super nice, you probably don't want to, you need a bit more trust than usual, right? So typical situation is a self-driving car. You're driving along the street, and the question is whether you can lift your hands off the wheel. It's very challenging. And now with AI doctors, in this case, you have 10 different AI doctors telling you that you should go through a surgery. Are you actually going to do that? Well, in this case, not surgery, it's chemo or radiotherapy, right? Are you actually going to trust these AI doctors without consulting a human doctor at all? It's quite hard, right? So this is all interesting motivations for trustworthy machine learning. So there are some interesting topics here, like OOD generalization, whether the model is generalizing beyond the training data. 2, explainability. Can the model explain the inner mechanisms, right? And 3, uncertainty estimation. So if the model doesn't know the answer or is not sure about the answer, then the model should also say, yeah, I make this prediction, but I'm not so sure, okay? And then evaluation is also an interesting aspect. If you try to evaluate machine learning models, you tend to produce some metrics like accuracy or AP or some detection rates and so on. But what are the right measures for trustworthiness? In a sense, evaluation is kind of connecting human needs with the algorithms for making some numbers, right? So how do you translate your need into some quantifiable metrics? That's not an interesting question here. So there are some other topics. So by the way, the previous 4 topics are the topics that I'm going to talk about in the lecture. But there are also other interesting topics in trustworthy AI that we do not cover in the lecture, although they are also very interesting and very relevant. So one is fairness. There are questions of demographic disparity, especially when the machine model is used for making someone's life different, right? Or it's recommending, like it's a matching system, let's say. So there are people involved, but let's say your likelihood of better match is increased for a certain demographic group. And some of the demographic groups are not in such a good situation, right? Then you have issues with fairness. Privacy and security. There are many interesting applications of machine learning where the data samples are coming from data subjects, like individuals who put their data online. Yeah, and then let's say ChatGPT is crawling all the data from your website, right? And then it has all the private information about you. And that information could, for example, pop up from any ChatGPT session with someone else, right? That's not you. And that causes a lot of privacy problems. So these kind of topics are also very important and interesting. There are a lot of abuse of AI tools, especially with very good foundational generative models these days. You can generate a fully realistic person face or or news content, right? And then you can disseminate it, causing a lot of societal problems. There are a lot of environmental concerns with especially also again with foundation models because they consume a lot of energy. There's governance issue where you try to come up with good regulations around the use of machine learning. Yeah, we only have 16 lectures, so unfortunately we're gonna not talk about these topics in detail, but just mentioning them as another set of interesting topics here. So now I'm going to talk about my own approach to trustworthy AI. So I like to kind of see this as a transition from what to how question. So what I mean by what task is, let's say, given an image, you try to come up with a label for the image. But that is not enough because the model is free to choose whatever inner mechanism to achieve this what question. It could look at the car body, which is perhaps more robust. I guess there's a slide for that. Yeah, causal and robust Q, but you can also use non-causal and spurious Q to make the prediction. There's no restriction whatsoever, apart from the fact that you're supposed to be good at in the training fit, right? So if the training fit is achieved by only using spurious Q, then there is no reason for the model to use causal robust Q. But eventually, when we talk about OOD generalization or a good explanation of the model behavior and so on, you want the model to be good at choosing the right Q for doing the recognition, for example. So the question is, how do you enforce that, right? Because, for example, if you have this novel situation where you have sort of an unusual situation where the frog is kind of flying on the ground, belly to the sky, right? Is it a frog or a car, right? And if you're relying too much on the background, then probably the prediction is just car. That causes robustness issues and generalization issues. And fortunately, the field is kind of moving towards this direction. So you see nowadays a lot of benchmarks in machine learning focusing on whether the model is using the right Q for recognition. So you do some kind of changes at test time to see if the model is still doing well in those cases. Also in the language domain, we now care about how the model solves the problem. So this is an example of chain of thought prompting. So you're not only asking the model to produce a good answer, you're asking the model to come up with the explanations of how it went to how it reached the answer. And when you do it this way, you also tend to get better answers, which is more correct. Okay. And more about my approach to the problem. So I like to conceptualize the how problem using this kind of diagram. So X is the input and Y is the output, right? And whatever happening in the middle is Z, which is a how variable, right? It could be the selection of Q or the inner explanation of how it reached the answer. I would say that machine learning 1.0 is more about learning the relationship between input and output. Well, this is for discriminative machine learning models. But in general, I would say it's X and Y problem. But now we are slowly moving towards X, Y, and Z problem, okay, where we need to also have a good understanding of how the model is achieving X and Y correlations. But the problem is when you look at most of the papers and most of the research approaches these days, you see that they are actually using XY data to achieve to learn the correlation between X and Y. Sorry, X, Y, and Z. So you're trying to solve the machine learning 2.0, but you're kind of still living with the same kind of data as before. And I feel like there are some limitations of how far you can go with the current kind of data. And for addressing this new type of data, you should probably think of new types of data. that achieve this new task, right? Okay, so for that, I'd like to mention a bit about data-centric AI, which came out in the context of still the XY problem, right? But my point here is that I'd like to take more data-centric approach to the XYZ problem, which is not a very popular idea these days yet, but I wish to kind of pioneer this way of approaching the problem. So to explain a bit more about data-centric AI, so it's kind of you can think of it as two different philosophies around improving machine learning models. So one is data-centric AI, and the other one, which is more popular, is model-centric AI. So in model-centric AI, what you do is you come with better model training algorithms or model architectures. Regularization, well, regularization is kind of in the middle. You kind of push the machine learning engineers quite a bit to come up with a better model and better optimization algorithm. But there are certain types of people who think that approach is kind of limited. And what you have to do is eventually to go back to the data and improve the data to actually improve the model quite a bit. And I tend to believe in that as well, because eventually the only source of information for the model is, well, not the only source, but the major source of information is coming from the data itself. And so there are some interesting tasks like, how to collect data better, or how to label the data better, and also how to make it more efficient, data collection more efficient. So active learning, course set selection, all kinds of like data set pruning or cleanup, all of these are very relevant. And also you have to kind of look for new types of data that could be useful for your task, right? And all of that are very interesting topics. And nowadays, it's even more important. Data-centric AI is getting even more popularity because of the foundation models. Because if you look at the foundation models, these are essentially data-centric approaches, right? Because you have to kind of come up with a good web-based training corpus, and then you employ a lot of engineers to resample and filter suitable data from the raw data. And eventually, so that's for the pre-training, and then eventually for fine-tuning and fine-tuning stages, you also use a lot of human feedback and human guidance for tuning the model further. And there's a lot of wisdom from data-centric AI coming in here. So this is so this is kind of a spectrum from general to specific machine learning models. So you have you start with some kind of self-supervised or some generic representation like foundation models in general, and then you can go to more specific models by fine-tuning the model towards your application scenario, for example, right? So that's a typical approach in many businesses and what data-centric AI is trying to achieve. And a lot of problems coming from the foundation models like hallucination, copyright issues, privacy issues, content filtering, these all stem from data as well. So if you want to really fix these problems, then you have to go to the training data and take a look at how things are working there and fix them. So data-centric AI for trustworthy AI, that's kind of the approach that I like these days. And I like to show a video of from ICSV 2 weeks ago. I hope the speaker works. So I made a 1-minute video on the work that I did last year. So eventually, it's me who made the video, so I can probably have a 1-minute speech on this So we are trying to make the models better with some untapped data that we have never used before. So maybe so this is the typical annotation scenario for ImageNet. You click on the image corresponding to the concept of the interest, but you normally have just true or false, whether you clicked it or not. But now we also flag the mouse trajectory and when and where annotators have clicked. And that information seems to contain where the object is in the image. Okay, that's kind of a free information, which is not collected, but just wasted. And now what we say is you should actually use that information for, for training the model further. So instead of just training the classifier, you have a second branch, which is doing the regression for the object location. Okay, so that's a very noisy supervision for the model. But when you train with that that extra signal, you actually improve quite a bit of the image benchmark from 81.6 to 82.5. And also on the OOD generalization case, you improve from 80.1% to 23.9%. So if you take like this data-centric approach, there's quite some mileage to go for free, because these are annotation byproducts, which are otherwise just wasted. So, by the way, the data set is there. So if you like, you can go to Hugging Face and download the data set, which contains all kinds of annotation byproducts. So the title of the paper is actually neglected free lunch, because I feel like these are literally free lunch, but no one is actually using it for now. For the other topics like explainability, with Elisa from our group, we have come up with we basically studied data-centric XAI, where task is actually to explain the current prediction of the model based on the training samples. So which training sample is contributing the most to the current prediction? Okay, and this is useful for finding erroneous labels, for example, in the training data, or for the typical samples as well. And so the conclusion of this paper is actually quite negative, which says the current existing training data attribution methods are very noisy and does not actually contain much information about the actual contribution of the training sample to the model. Also, the other conclusion is it's probably a wrong question in the first place. The model tends to be very stochastic. The training is very stochastic, so including or excluding one sample from the training data doesn't seem to influence the model so much. So we should probably ask another question or look into very specific cases where the training samples are actually contributing significantly to the final result. So that's kind of not a method paper, but more like thinking about what is the better way of doing it, or are we asking the right question kind of research. The other type of data-centric trustworthy AI research we're doing is for uncertainty estimation. So we came up with a representation learning scenario where the representation is now more suitable for uncertainty estimation. So, and now representation learning is another interesting data-centric approach where you can now tune this model to your application scenarios with your own data. Okay, so these are a type of research that we do, and the 5-year research aim for me is to actually enable quantum jump in productivity using machine learning. Well, it's now a 4-year research aim because the slide is from last year. But I guess we are getting there slowly, not like 20% so far, I guess, but we'll see more acceleration in the future. So the group is growing. We have 8 people here, and the ones with red circles around, these are they are tutors and lecturer. So we have Palintir, who's the tutor, and Evgeny is there. Yes, another tutor. Right. I guess Arnas is not here, I guess. Okay. So this is our group webpage. So a lot of people ask me, why do you put scalable in front? Okay, because people hear about trustworthy AI, but not so much about scalable. So scalable here means I wish to take a more data-centric approach, and I believe what makes an approach scalable is by using data rather than hiring engineers to tune the hyperparameters and so on. So here, scalable actually means the solutions that we are pursuing are actually working in the real world, and it has to be efficient and can be applied to large-scale models like foundation models these days. And the technique should have high impact in academia and industry. And there are some research principles for scalability that I have learned on the way, which is most importantly, simple is better than complex. Second, you have to understand before solving a problem, because without understanding, you're not, your solution is very short-lived. And also, you should not follow a dead end, because like, if you can see far into the future in this research field, you're kind of fundamentally limited by certain lack of information, for example, then I wouldn't really go into this dead end. Instead, I would just build a new field and pursue what is more likely in this new field, okay? Again, these are topics for the course. I think I talked about it. Registration. So if you have not registered for the course yet, then please go ahead and register here. By the way, the slides are online on the webpage, course webpage, so you can access the slides and click on the links here as well. Yeah, please finalize the registration before the submission of exercise 0, right? That is on 22nd of October. This is the rough schedule. We have 12 lectures. We have 3 parts. 1, OOD generalization, explainability, and finally, uncertainty estimation. We have 3 exercises corresponding to each part. We have a Christmas break after 11th of December, and we resume on 15th of January. Yeah, and then the end of course is around the end of January. Okay, I'm going to talk a little bit more about tutorials. So I have booked lecture 7E02. I don't know exactly where that is, but should be here. On Mondays 10 to 12 after this lecture for now. So there are 2 types of tutorials. One is exercise recap, which is, I think, more important. So after submitting the exercises, we're going to grade them and return them to you. And we're going to have one feedback session where we explain where you lost the points and what are the common mistakes, and in general, how to approach the problem. Okay, and how to approach the exam questions, which should be similar to the exercise questions, except for the coding questions, maybe. But we are also going to have Q&A sessions in the same slots for some of the weeks. It's not going to happen every week, and it only happens with prior notice. So the notice could happen before the lecture, or it could be put on the Discord channel. Right. But then the other problem here is that I heard that this clashes with the math for machine learning course. So how many are taking this course? Okay. Yep. Then sounds like we have to find an alternative slot for that. So okay, I'm going to ask the lecture hall manager, who's kind of booking the room, and see what is a suitable slot. Yeah, I'm gonna ask you again on Discord or something. Okay. Yeah, on Discord. And these are exam dates. So exam 1 is in February, and exam 2 is in April. But the exact date and location will change, perhaps. There are sometimes like clashes with other exams, and they ask me to change it all the time. So yeah, so lecture times Mondays from 8 to 10, but we start at 8:15. That's the norm, I guess, here. The first session finishes at 9, and then we take a small break and then resume. Okay. And the aim is to finish before 9:50 to allow you to go to bus stops and so on, take the bus. You can always use Discord for offline Q&As. Communication is through emails in Discord. So if you are not on Discord yet, please ask me. Yes.
The choice will be sharp or this what's happening with
The tutorials.
yeah.
Yeah, the tutorials can also follow the usual practice. Yeah. Yeah. Makes sense. We can wait for 50 minutes. Discord, yeah, we're going to distribute the invitation code in case you don't have it yet. Just write me an email or something, okay? Grading policy. So this is the diagram, right? So first you have to register and then submit your exercise 0. There's no like score threshold or whatsoever for exercise 0. It also doesn't count towards your grade anymore. All you have to do is just to submit it, okay? I think submission is a quite a big hurdle for some of the participants here, because yeah, we really wish to have students who are keen about the course, so we put this kind of minimal threshold. And then there's going to be exercises 1 to 3. And there, the requirement for you to actually take the exam is to get average 60% from the exercises. So if you register and submit exercise 0 and get over average 60% from your exercise 1 to 3, then you're admitted to the exam, if you like. And then during the exam, you're going to get exam scores. That's going to be the raw score from your exam. It's scales from 0 to 100, and there's going to be an independent pass threshold for the exam. So you should get more than 50% from the exam score in order to pass the course. There's going to be 2 exams, exam 1 and exam 2. One in February, the other one in April. You can choose between the 2, basically. But if you take the first exam, then on principle, you cannot take the second one, unless you fail the first one, okay? I think this is also standard here, so you all understand how it works. Yeah, so there are basically 3 cases. You take exam 1 and pass, and exam 1 score will be the final score. If you sit exam 1 and then fail, then you have another chance to take the second exam, okay? And third case is you can basically just choose to take exam 2 for whatever reason. You can just choose it, even for personal reasons. Yeah. Final score is also different from the exam score, because now you're also including the topics from the exercises. So 60% is the threshold for you to take the exam, right? But any score beyond that is going to be added as a top-up to your exam score. But the ratio is if you get for extra 40% from the exercise, then that's going to translate into 10 extra percentage points for your exam score. But then if your exam score was 100% or over 90%, then you're probably not going to enjoy the full 10% on top from your exercise, because there's also a cap on 100% for your exam score. Okay, so that's basically what these equations are showing. You have linear scales from the top-ups, and then where the maximum is 10%, and then you have a cap at 100%. Okay, so even if you just pass the exercises, if you're very good at your exam, then you can still get the best score from the course. Eventually, the final score is going to be translated into the final grade system from 1.0 to 5.0, where 5.0 is the fail and 1.0 is the best score. Or is it the other way around? Is the right? Yeah. Exactly. Yeah. But for this translation, we always do it post-hoc. So we look at the distribution of scores, and if the exam turns out to be very hard, then we also make it a bit more easier. Yes.
But there's no intention to make a second exam, because in second classes, they tend to sound like
yeah. So yeah, so that's the plan. So we're gonna make the second exam harder. Thanks for asking. Yeah. Because otherwise, yeah, exactly. Otherwise, it could be unfair. Some boring disciplinary topics, but very important. Plagiarism is not allowed. You should not misuse machine learning and data, especially you're advised against using privacy-related data. Free riders in exercise groups. I'm going to talk about exercise groups later. If there are members of the group who are not contributing too much, then you should always report to tutors or lecturer, and we're going to look into the case and assign fair grades, fair scores for the group members. Late submissions are not allowed, obviously. Yeah, this is something new this year, actually. Use of language models. You're allowed to use language models, but with a lot of caveats. If you use the language model for generating any exercise, then you should be very clear about which language model you used and which part of the answer is based on language model. Okay. And also verification and academic integrity. You're responsible for the outputs from the language model, and you should verify the truthfulness and the true source of every output from the language model. And failing to cite some sources will potentially result in disciplinary actions as well. Could be seen as plagiarism. So you should be very careful with the academic integrity here. The other advice in here is diversity and personal touch. The answers from the language models tend to be very uniform. So if you want to avoid submitting very similar solutions to other groups, then you should probably want to add a bit of personal touch and your personal anecdote or personal opinion and so on. And also do not rely on the language model output for verifying your solutions, because they tend to just say, yeah, you did a great job, right? So you should be, the critical thinking is for still your job. So exercise 0 should be submitted, yeah, for that base. Yes, groups. Group size will be 3, unless there is a good reason to have other groups, like groups of 2 or 4. If you have a good reason for that, please come to us and discuss with us. There are 2 ways of forming the groups for the exercises. One is you just choose your group amongst yourselves and then let me know which group you came up with, right? Before 29th of October. The second option is just to wait until 31st October when we will assign the rest of people to random groups 3. Okay. So if you have a strong preference, please do submit this preference before 29th of October. And this is an instruction on how to submit an exercise. All the exercises will be based on Google Colab. So that's the link for exercise 0. And so this is briefly how you should submit an exercise. You copy the Colab file to your local Google Drive, and then work on the solution there. Pin the version for submission, and then share your local Colab with our email address before the deadline. Okay. Yeah, I'm going to explain step by step. So this is how you copy the Colab file to your local Google Drive. You have save a copy in Drive, right? And then you work on the solution. And then this is also quite important, because if you just share your file to us, then we have no way to, well, we have a way to kind of see whether you made a change after the deadline, right? But you also want to kind of declare which is the final version, right? So otherwise we have to kind of look at the final version before the submission deadline, and then yeah, it could be, yeah, you should have the control over which, like, deciding what is the final version for the work, right? So for doing that, you click on this all changes saved, right? Or last saved at blah blah, right? And then you're going to see a list of basically comments, right? And then you click on the version that you like to submit by clicking on this ellipsis on the right, and you should have this name this version option, right? And then you can type in submission here, and that's it. And then you share the file with us. Okay, that's how it works. Yeah, with this email here, and yeah, viewer is sufficient, so you can just put viewer here, viewer access. Exercise frequently asked questions. So can I use high-level library? So thanks for asking this question 2 days ago or something on Discord. Yeah, the thing is, you may lose points if you rely too much on high-level libraries, obviously, because it does not show whether you're understanding the mechanisms, right? So whenever possible, you should rely on more basic libraries like NumPy. So example 1 is you have the task of splitting the data into train, val, test, right? And actually, the scikit-learn has a nice package, nice library for doing that automatically, right? But then you're not showing that you did the job by yourself, right? So in this case, what is a recommended choice is NumPy random choice, for example. Another example is the loss function for your network cross entropy. And actually last year, some people submitted to work with f.cross entropy, right, for completing this exercise. And this is not good because you're actually asked to implement the function. So you're allowed to use like addition, multiplication, or simple functions like torch log or torch x. But you're advised against using cross entropy, which may lose you some points. Okay. There's a book on the course. So last year's materials are compiled into book, which is great. Now you can also take a look at the full lecture notes from last year, or read about some more materials with this book. So the credit goes to Balint, who's sitting here, who did most of the job here for making the book. But the caveat here is that a lot of materials have changed since last year. So if you just rely on the book, then you might miss quite some materials. And we take a break now for 5 minutes and then resume prerequisites for the course. So, prerequisites for the course. The exercise zero materials are kind of preparing you for the course. So one is multivariate calculus, which will be very important for the course. Machine learning concepts like the basic concepts and PyTorch. So I'm going to cover a bit of multivariate calculus and machine learning concepts here. And the green dots, green square on the top right corner indicates examinable materials. So far there's been no examinable materials for the exam, but now, yes, this is part of the examinable material. So for multivariate calculus, I like to introduce this connected delta function. How many of you know this connected delta? Okay, that's easy. Okay. So yeah, it's 0, 1 function indicating whether the indices are equal or not. And obviously, if you derive a scalar against another scalar with both with indices, this results in connected delta, right? So only if the indices equal, then you have 1, otherwise you have 0, okay? And if you derive a tensor into another tensor where the indices are all free, right? Then this is going to give you products of connected deltas, okay? Which means this is 1 if and only if all the indices are actually equal, okay? Now using this, well, before using that, another prerequisite material, which is to turn a linear algebraic expression into scalar expressions. So this is like matrix multiplication. C has 2 axes, right? I and j, right? And how do you write individual members of this C matrix based on the individual members A and B? Okay, so you can now write Cij as the summation over the scalar products of each member of A and B, where the index is linked between A and B with the adjacent indices, right? So A and K and then B to K multiplied and then sum over K. By doing this, you can turn any linear algebraic expression into scalar expressions, and this is a magic solution that kind of lets you do multivariate calculus with just tools for single variable calculus, right? So here's another notation here. So the other notation is the gradient of a scalar function based on vector inputs, right? So f is a function from vector space to a scalar space, to a real number. And here what you take is the gradient of f with respect to individual indices of the input vector, which is indexed by I here. And you can write, so the delta f, how do you call this, delta f, or what's the way? Delta f? Yeah. Del f? The del f is a vector, basically, and each member of del f is the derivative with respect to an individual variable. You also have Laplacian. Do you call this Laplacian on the right side? Okay. Laplacian of f, which is the summation over the second derivatives of f. Okay. So we'll probably use this notation. By the way, yeah, Laplacian f is a scalar, not a vector or matrix. You also have Hessian, which is a matrix. Do not confuse Hessian with Laplacian f. Okay. Well, Hessian is basically you have free variables for second derivatives. So you have the free index for the first derivative, and then another free variable for the second derivative, and you have all possible second derivatives of the function, and you have Hessian. So now there's another rule, so which is to kind of eliminate summation with connected delta. So when you have a very complex summation here, you can actually delete one Kronecker delta with one summation. How you do it is basically you identify which indices the delta has, I and D, right? And actually I is here, right, in the summation, which means you can actually delete I here and delta here. And instead, you replace all the i's in the equation with k here. Okay, so now this becomes summation over j and q, and the I is replaced with k. Why is that? Because the summands are 0 when I is not equal to p. So when I is not equal to p, you just drop them, and for the case where I is exactly equal to p, then you can just replace I with p, right? And you're not summing over I anymore, just sum over j and q, the remaining indices. In the second case as well, you can do the same. Delta ij, right? So delta ij can be deleted here by replacing all i's with j's in the remaining summands, right? And removing the summation over I. So now we have xj squared log summation over k x of a jjk, where there's no I anymore. Using all of these ingredients together, you can show interesting results in multivariate calculus. For example, you can say that if you take the derivative of squared L to norm of a vector, you get 2 times the original vector. You can take a look at this by looking at individual variable of the gradient. Okay, so if you take the derivative with respect to x first, and then you can write this as a derivative with respect to xi, and you can just write down the L to norm as a summation of squares, right? And by the linearity of gradient, you can swap the summation and gradient inside. And by using chain rule, you can say the derivative xj squared is basically 2xj times the derivative xj with respect to xi. And if you remember correctly, this is exactly Kronecker delta ij, right? So you write down delta ij. And then now you can remove the summation with delta and replace all j with I, and you end up with 2xi, right? So we used all the ingredients from previous slides and linearity of gradient to reach this conclusion. You can do more complicated derivatives. For example, derivative with respect to matrix here. If you derive a trace of A with respect to the original input, your derivative will essentially be a matrix, because the input is the matrix. And you can write down the matrix as the derivative as this way. And the trace is basically the summation over the diagonal entries. And again, you can swap the gradient with summation due to linearity. And again, their derivative akk with respect to aij is basically delta ik and delta jk. And now you can remove k from the equation by replacing k with j, right? If you decide to remove the second delta, right? And you end up with delta ij. In matrix form, delta ij is just an identity matrix. So you can conclude that if you derive trace A with the input matrix, then you get identity matrix. Yeah, it's more complicated. Again, the trace of AB can be written as A times B, where the middle, the adjacent indices are equal. But now this is trace, so you also make the outermost indices equal to each other.
and sum over both P and Q. And you bring the derivative inside the summation and then use the product rule for gradient, taking gradient, right? And then you end up with delta IP and delta JQ and BQP, where you can remove all the deltas with summation and you end up with BJI, which is the index for, which is the value for index IJ for B transposed, right? So you can write B transposed in this case. So the ordering of indices also matter a lot. Yeah, this is a typical quadratic form that appears a lot in linear algebra. Again, you can also write down the X transpose AX as a product sum, right? And you bring the derivation against Xi into the summation, and you do product rule. You remove deltas, and you have more simplified form of products, where you end up with A times X and A transpose times X. Okay, and this is the solution. So that's it for multivariate calculus. I find multivariate calculus very easy when you can actually turn everything into scalar calculus. Machine learning basics. What is generalization? I think many of you just know what generalization is. In a nutshell, it's basically whether the rule that you find during using the training data or whatever resources, it actually generalizes to new situations. There are some different types of generalization. Some people care about IID generalization because they believe they have good representation of the test distribution in the training distribution, right? So all that matters is whether you generalize well to new samples from the same distribution. So I give some examples like on the rightmost column, like IID is the case when you try to recognize the same person who's always at the office. But OOD generalization becomes more interesting. I tend to give you like those three different possibilities for OOD generalization. First is cross-domain, second is cross-bias, and third is adversarial. The task remains the same, all the case. You try to recognize the person, but in different situations. So for cross-domain, the task is to recognize the person for the first time in party costume that you have never seen before. Cross-bias is a little bit more tricky because you might have overfit to some other factors that are not essential for the identity of the person, like the clothing. And now what happens in cross-bias generalization is people basically swap their clothing. And can you still recognize the person if you are relying too much on the clothing of the person? Adversarial situation is a little different situation where there's a player against you. Maybe the person who's being recognized is trying to swindle you, right? Because of whatever reason, because they probably want to pass the face recognition system and you're not part of the company and still wants to get into the company, right? And what they do is they wear some face mask or whatever tool they can come up with to mislead the system into thinking you're someone who's not. Okay. So these are the generalization scenarios. There are some more machine learning basics here: training set, validation depth set, and test set. I think you all know what this means, right? But I also want to give you more perspective, like perhaps new perspectives on these splits, because I don't like following what people have been assuming for these splits. So the general philosophy behind training, val, test is that train, build your model. Training is for building your model. Validation for simulating deployment. So you're basically having a fake situation, like a fake replica of the test where you can actually choose your right model or choose hyperparameters. And test is for the next level where you actually simulate the test deployment, right? So actually there are multiple stages. So there's a final deployment scenario that you care about, for which you actually don't have any data. And for simulating that, you have a test split, right? Which you don't probably want to touch too much, because as you touch it so many times, then it becomes not so much like deployment scenario anymore. And then there's validation set, which is a simulation of the test set, right? Which is another kind of simulation of simulation, where you can do more stuff, right? Like choosing the hyperparameters or making design choices. And then there's training set, which doesn't have to be anyway in any way similar to validation or test set, or right. With the training set is just for training your model, right? And what seems to matter more is to have more data there. So if you can also have the kind of data which is very different from the deployment scenario, because you believe such data will actually help you build better representation, for example. I'm just talking about typical ways people approach these splits, not necessarily showing my understanding of these splits, which I'm going to talk about later on in the course. So in each split, people tend to do some kind of optimization procedure, right? So typically they optimize different parameters with different objectives, with different optimization algorithms. So for training set, they tend to optimize model parameters, like millions of or billions of parameters, with the objective of fitting to the training set. And optimization algorithm is typically gradient descent with TPUs, GPUs. It could be Adam or SGD or whatever variant of Adam and so on. And the optimization frequency is like every step takes like millisecond to a second, depending on how large your model is. But now with the validation set, the optimization frequency is much slower, because sometimes you have human in the loop. Like there's something called graduate student descent, right? Where PhD students sit in front of the computer and try to come up with a good working setup for your model, right? And in that case, the update frequency is like hours to days, right? You have to wait until the model is trained, and then if the model doesn't train well, if you look at the loss curve and you realize, yeah, this is not working well, then you stop it and then go back to the hyperparameters and choose better learning rate or whatever. So this is all happening on the validation set, and typically use the set for tuning hyperparameters. And the objective is to make the model generalize better to this validation set. Test set is still like validation set, but you have much less. You typically put much less freedom for updating your hyperparameters. You can still tune hyperparameters there, but you're advised against doing it too much, because if you do it too much, then it becomes more like a validation set rather than deployment scenario. And also, test sets are kind of defined by the benchmark builders, who are kind of different, like researchers from other labs, for example, who build a benchmark and invite people to record their performances on this benchmark. Okay, they typically put some rate limits or how frequently you can submit your model to the system. Yeah, and also these people tend to update the so here I wrote down paradigm shift and update evals standard. So what's happening is they also update the test set to reflect new kinds of needs from the application. But also what people can do is they can update their own approach to the problem, for example. And this is happening much more slowly, like from months to years, okay? So that's kind of the update that's happening with the test set. So test set is still something that's moving over time, but very slowly. validation set is moving, the optimization of our validation set is moving more frequently, and training set is moving, training set update is very frequent, like milliseconds. PyTorch, you can just follow exercise 0 and you should be able to have a good working code for PyTorch. And I think that should be sufficient to get you ready for the course, for the rest of the exercises. So that's it for the introductory materials. And I'd like to go into the first part of the lecture, OOD generalization already. Okay. So this is a video again for showing why do we care about OOD generalization. I'm not sure if I have so this is self-driving car which made a problem. Sorry. There's no time. Sorry? 321. 321. Thanks for that. Yes, this is it. Then yeah. So obviously the model hasn't seen such a structure on the road so frequently. So yeah, in this case, this was a bollout, so there is no big issue. But imagine if it's a person or right cyclist, right? Then you run into a lot more problem. Another example is the future prediction. When something really unusual is happening, like COVID, right? Then your prediction model is not going to work as before, right? To take care of this, people tend to retrain the model and readapt to the new data distribution. And then your accuracy kind of remains above some threshold, which is kind of minimal threshold for making it relevant. This is called MLOps, right? It's costly because it involves humans and very intelligent humans like machine learning engineers. As I said, it's like 100K euros per year. Not only that, but you also need to use GPUs, right, for that. So the electricity is super expensive as well. 25K euros per year for GPUs and 8 tons of CO2 per year. And you also need to manage data, which is also very expensive and time consuming. The core reason why people do MLOps is because the data is shifting and you have to adapt to the new data stream. So there's a collaboration between data engineers, data scientists, and DevOps people, backend engineers, perhaps front-end engineers. You need some input from humans for re-annotating data, for example. And machine learning scientists for incorporating new techniques here. Very expensive. So the goal here is to reduce the costs and automatize as much as possible. So level 1 is when you do not care about machine learning at all. So there's no machine learning model. You do it with some code or you do it by hand. So this is the case when you have like a center with hundreds of employees, contractors who are kind of receiving phone calls from customers all the time, and they take care of things by their by access to the database, by typing themselves, right? But now we introduce ML, right? And the model now learns to generalize to some other data, but only to the same distribution based on the annotated sets. Even in this case, you need some human input because you need to adapt to new cases. And whenever there's a new case, like every month or something, you invite people to annotate those new samples, a few of the new samples, and feed this new sample into the training set for the next batch of models. This is, let's say, level 2, and then there's level 3, where you have much less frequent update of the model because the model is now more resilient to small changes of distribution. Level 4 is where you do not need any annotation anymore. All you have to do is, for example, you prepare a lot of models, and all you have to do is choose the right model for the current distribution. So whenever there's a new kind of situation comes in, you already know that this could have happened, right? And you have prepared a very diverse set of models. So all you have to do is to choose the model or train a very lightweight model, which is kind of choosing the right model for the type of program. So there's quite some trend towards this level 4 kind of machine learning in the OOD generalization field. So we're going to talk about a little bit of that as well in the lecture. And the final level, I would say, is there's no MLOps anymore. You don't need to hire any engineer. No machine learning expertise is needed, which is super cool. Even the machine learning engineer functionality is fully automatized, right? The hyperparameter tuning and model selection is also done by the model by itself. I'm not sure if that's really possible, but that's sort of the goal that we are aiming for, reduce the human involvement as much as possible. Level 5 is kind of used to be thought to be kind of very far away from now, but now with the language models, it's actually becoming more reachable, I would say, because language models are giving very nice interface for people to kind of adapt the model to their task instantly using, for example, in-context learning. You give the model a bunch of examples in the prompt, and the model on the fly learns how to perform this task, right? So all you have to do is to speak English, right? Because if you use other languages, probably it doesn't work as well. If you can formulate your need in English and collect a few samples for your use case, then you're good to go. I would say this is very close to level 5. But at the same time, language models are not solving all the problems in the world, right? It doesn't solve computer vision problems well. With the GPT-4, maybe there's a possibility now, and probably next year I'm gonna delete this slide altogether and say, yeah, it's there. But for now, it looks like we are still not there. And yeah, for different verticals, we have different levels of achievement so far. Yeah, human effort, very costly. And once we reach the level where we solve the OOD generalization, your model will work well in new situations. Small businesses can do their business with machine learning without spending too much money. The model can be extended to more risky applications where you cannot tell what kind of new deployment scenarios the model will face, right? Like self-driving car. You are probably more confidently driving with the car if you know that it's generalizing well to new situations. So the first part of the part 1 is definitions and evaluation, which is very important to define what we eventually want, right? So what do we exactly mean by OOD generalization? So that's the starting question. This is when the deployed environment is different from the development environment. So this is an example of self-driving car. So your training set for the self-driving car is like rural, very less traffic, countryside kind of scenes, and then eventually the car enters the city, and let's say you have not prepared the model to do well in this situation. So that's a typical OOD generalization setting. For that, I wish to define a few terminologies here. Machine learning setting. We care about deployment of machine learning in real world. And what I mean by machine learning setting or setup is the specification of available resources and surrounding environment for a machine learning system. So we have two settings. So one setting consists of the specification of two environments. One is the development environment and the other one is deployment environment. Okay. For example, for in-distribution supervised learning, development scenario means development scenario consists of label samples, X and Y pairs, from some available distribution, P distribution. And the important thing is that for the development environment, the data stream is coming from the same distribution. So if you specify this, then that's one setting, which is kind of describing what in-distribution learning for discriminative task is, right? So we have development stages and deployment stages. Development stages for preparing a machine learning model for deployments. And that the development involves not just training, but also validation, okay? And through validation and training, you finally decide which model to deploy, right? That's your final decision. And then the model goes to the deployment and it operates there, okay? Deployment stage is when the actual users use the model. That's prepared from the dev stage. Yeah. But actually in common practice, people do keep track of the performance in the deployment stage. So a bunch of machine learning engineers prepare some direct or indirect metrics of how the model is performing in the deployment, and then tracks this this measurement to see whether the model is doing the right job. So in practice, actually, so this means you still get some information from the deployment to change the model in the development stage. So the boundary between deployment and development is quite blurry in practice, actually, because you're also using data from deployment to alter the model in the development stage. But for this course, we're assuming we have a simplifying assumption where these two stages are actually distinct, and all the model decisions are happening in the development, and eventually you choose a model from development stage and then deploy that to the model, and that's it. Okay. So when you try to specify the resources for the development and deployment stages, you have to talk about data. Data is very important. So it's not just training data that you have to talk about, but you have to write down all kinds of possible resources available during development. That includes data sets, but also labels that's put on the data set, data samples, which type of data set it is, and also any kind of guidance for. So there will be some humans involved for training the model and their expertise, right? And their inductive biases or assumptions about the problem. All of these are kind of part of the resources for the development. So it's not just training data, but also the human knowledge and expertise, everything put into building the model. Environment for deployment, yeah, you have to specify what kind of distribution the model will face, okay? And there's a concept of real-world environment. If you just talk about machine learning settings, then it can get very boring and very detached from the actual application scenarios. So when you explain yeah, I'm working on the under the OOD generalization or cross-bias learning, for example. Then you typically also talk about, you give an example of what kind of, in which kind of real life scenario is this setting relevant, right? So a few minutes ago, I also gave an example of cross-bias generalization with human recognition as an example, right? So that's a good example of real world scenario. Another example I give here is basically wafer defect detection. So you get kind of visual sensors on top of the wafer plates, and you build a data set of defective and naive or normal samples of wafers, visual data sets. And you assume that the sensors and the production line does not change at deployment. In that case, we can say, yeah, this is in distribution supervised learning setting. Or the other way around, if someone comes to you and, yeah, please explain to me what is an in distribution learning supervised learning setup, then you can also come up with this example to explain what you mean by that. Evaluation benchmarks are important. So far that was about machine learning settings and environments and so on. Now I'm going to talk about evaluation benchmarks and evaluation protocols that are supposed to test the model performance in some designated machine learning setting. Okay. For research and development, evaluation is very critical. I think you all know that, right? Because this is kind of a simulation of what's going to happen in the deployment stage. And this is where you do model selection and you also track progress, whether you have been improving at all. You can also benchmark against competitors. And by using this, you can go to investors and say, yeah, we are doing better than the competitors, so we deserve the money that you are going to give us. So these evaluation benchmarks can also simulate different learning settings, learning scenarios. For example, you can build a benchmark on ID generalization, or you can also build a benchmark on certain type of OOD generalization. For building a benchmark, people have to come up with the data set, first of all, but also evaluation metric that's going to be used for this benchmark. In which rule you should use the data sets, right? You're allowed to use it this way, or right, you're not allowed to use the test set for training the model, for example. And also you should, very importantly, you should also set out the rules for using other sources of information than the designated data set. This is something that a lot of people miss, and they also tend to use other sources of information than what they are allowed to use. For example, when people use pre-trained model, like ImageNet pre-trained model, the benchmark should also make it clear whether the competitors are allowed to use this kind of pre-trained model for competing in this benchmark, right? Otherwise, people can just come up with click model or other kinds of large-scale models, which is trained on a huge amount of data, and say, yeah, our model is working better than yours because of this and this, right? But eventually, what really made them work better is the pre-training data set, for example. Or even worse, the pre-training data set could contain the test data itself. And then there's no point, right, in saying, yeah, our model is working better than the others. So what is the relationship between the machine learning settings that I described before and the evaluation protocol or evaluation benchmark, the data set splits? In general, the development data and deployment data are mapped to respectively train plus file and test, okay? The thing is, machine learning problem can get artificially easier if information from the deployment stage is available during development. So in the most trivial case, the deployment data is actually the sample-wise available during development. That is not machine learning anymore, right? Because all you have to do is just memorize or store it somewhere, and then at test time you just give it, right? It's still easy when it's ID generalization if the distribution does not change. I'd say it's medium difficulty when there's availability of less number of samples from the distribution during development, for whatever reason, for the cost reasons or whatever. It's harder if there's a distribution shift between train val and test, right? And very hard if you don't actually have any information about the deployment distribution at all. So the difference between hard and very hard is whether you kind of have a broad information about where the model will be deployed. For example, if you know that the model will be deployed to city views, then probably you can do something about that. So for the core principle in formulating a benchmark is the dev data should be clean of deployment data, because otherwise it's not machine learning anymore. And any information that is allowed during development or about the deployment that is available during development should be clearly defined and communicated in the evaluation protocol. So in other words, train val should be clearly separated from the test. And inherently, the evaluation protocol does not actually care too much about the way you use the train versus val during model development. Okay. I'm going to talk about that later in the later slides. So actually the time is up, so I'll stop here and resume the rest of the materials from next week. Okay. See you next week.